faithfully conveying value, interpreting great books from around the world. Hello, this is Sally's Book Club. Today we're exploring The Giant of the Infinitesimal, subtitled The Extraordinary and Amazing World of Nanotechnology. A nanometer is a unit of length. 1 nanometer equals 1 billionth of a meter. The diameter of a human hair is about 60,000 nanometers. Nanotechnology studies matter and phenomena at the nanoscale. Though invisible to the naked eye, nanotechnology is transforming our lives through research breakthroughs. Imagine films thinner than plastic supporting elephants, color-changing clothes, or extracting fuel from air itself. These seemingly magical examples are nanotechnology achievements. Exactly what this book reveals. The authors are British scientists Peter Forbes and Tom Grimsey. Peter is a professional writer contributing to publications like Scientific American. And then Tom, originally a sculptor, joined a nanotechnology project developing educational tools to showcase nanoscale wonders. The book's 10 chapters cover nanomaterials, phenomena, and applications across fields. We'll explore materials, phenomena, and applications using concrete examples. First published in 2014, I'll include newer developments to enhance your understanding. All right, let's discover nanotechnology, the giant of the infinitesimal. A key nanotechnology goal is developing advanced nanomaterials, with carbon nanomaterials being particularly valuable. Carbon, element 6 on the periodic table, is everywhere. Charcoal in stoves, pencil graphite, and more. Though carbon seems ordinary, 3 nanoforms are absolute superstars. They're fullerenes, carbon nanotubes, and graphene. Before introducing these 3 siblings, let's understand allotropes. Allotrope means the same element with different forms. Shiny diamond and dull graphite are both carbon, but have totally different shapes and properties. They're 2 allotropes of carbon. They're 2 allotropes of carbon. The reason they're so different is because of how their atoms are arranged inside. In diamond, carbon atoms form a tight 3D structure, so it's super hard. Graphite, though, also carbon, is one of the softest minerals. If we magnify graphite, we'll see it's made of stacked graphene sheets that slide super easily. That's why graphite blocks break or crumble easily. Those 3 carbon nanomaterials we just mentioned are also allotropes of carbon. All right, let's dive into their discovery stories and unique properties one by one. First is fullerene, a tiny ball of connected carbon atoms. Its diameter is under a nanometer. Placing one on a soccer ball is like putting a soccer ball on Earth. The discovery of fullerene came from interdisciplinary inspiration. In 1985, Dr. Croteau from the University of Sussex in the UK found a new molecule in an experiment. Using chemical methods, he figured out this molecule had 60 carbon atoms. But how are these 60 atoms connected? He couldn't crack it and was really frustrated. Croteau imagined all sorts of possible connections, but nothing worked well. Then, by chance, he read a paper by Fuller, an amazing architect. In that paper, Fuller explained how to design spherical domes, and it sparked Croteau's idea. He realized the 60 carbons might form a sphere, like Fuller's domes, and calculated it should have 20 hexagons and 12 pentagons. Guided by this, Croteau got help from peers and proved the atoms connected that way. So they named this carbon ball fullerene. Fullerene has awesome properties, like an inner cavity. Adding other atoms there gives it superior traits. For instance, in 2015, scholars at Oxford University successfully inserted a nitrogen atom into a fullerene. In this material, the spin lifetime of electrons can be significantly extended. This physical property allows such fullerenes to be used in creating highly precise navigation devices. Later, researchers auctioned off this special fullerene. A 200 microgram sample sold for $32,000, equivalent to about 1 billion renminbi per gram. This indirectly demonstrates that research on carbon nanomaterials has enormous commercial value and potential. Speaking of the discovery of fullerene, there's actually a little anecdote here. As early as 1980, a Japanese scholar named Sumio Iijima used a special electron imaging microscope to photograph fullerene. The photo showed a ring-like structure, but because it was a flat projection, Aijima didn't realize it could be a sphere, so he unfortunately missed the credit for discovering fullerene. However, Aijima didn't get discouraged. He continued researching carbon materials until 1991, when he made another major contribution. That year, he published an article stating that he had discovered a tube-like carbon material. These small tubes were later named carbon nanotubes. Carbon nanotubes are essentially hollow tubes with walls made entirely of carbon atoms. The diameter of carbon nanotubes ranges from a few nanometers to tens of nanometers, and they can be made extremely long. Scholars at Tsinghua University once created a carbon nanotube half a meter long. Since Professor Iijima discovered carbon nanotubes, this material immediately became a favorite in the research community due to its excellent properties such as high mechanical strength. A single nanotube can theoretically be over 100 times stronger than steel. How can we understand this strength comparison more intuitively? Imagine a large suspension bridge. The span of such bridges has limits because steel cables would eventually snap under their own weight if too long. To date, the longest suspension bridge humans have built is the Çanakkale Bridge in Turkey, with a span of 2 kilometers. Steel cables have a theoretical limit of only tens of kilometers, but carbon nanotubes can be stretched to 5,000 kilometers at sea level. Scientists have long dreamed of creating a space elevator directly from the ground to a space station to drastically reduce the cost of transporting materials to space. Among all materials, only carbon nanotubes can serve as cables for such a space elevator. So, if we could build a carbon nanotube bridge, it wouldn't connect riverbanks, it would connect Earth to sky. For quite some time, fullerenes and nanotubes dominated nanotech research until 2004, when a new material stole the spotlight: graphene. In 2004, Professor Geim and his PhD student Novoselov from the University of Manchester published a paper announcing they'd created carbon flakes, atoms arranged in hexagons, just one atom thick. This material is graphene. Scientists long believed single-atom thick materials couldn't exist stably, but Geim's team shattered this assumption. Their approach was surprisingly simple. Start with graphite. They stuck graphite between two pieces of tape and pulled them apart. Here, the tape's adhesive force overcame the bonding between graphite layers. Each stick and peel action split graphite into thinner sheets. By repeating this with fresh tape on thinner pieces, they reduced layers until achieving single-atom graphene. This sounds easy, but required extraordinary patience. Legend says they peeled tape for over a year, a modern grinding iron rod into needle persistence story. Graphene immediately captivated the world with its astonishing physical properties.
It's now the world's thinnest yet hardest nanomaterial, 200 times stronger than steel.
What does that mean? To pierce a perfect graphene membrane with a pencil, you'd need an elephant standing on it. Plus, graphene is nearly transparent and conducts electricity better than silver or copper. That's why countless researchers study graphene, and governments invest heavily in its industrial applications. In recent years, graphene keeps popping up in the news. You could say it sparked a nanomaterial gold rush, or, as the authors call it, a carbon rush. For example, the book mentions graphene DNA sequencing, super fascinating stuff. DNA, deoxyribonucleic acid, is life's primary genetic material. It's a long chain of 4 base types. Reading their sequence is crucial for biology research and disease detection. DNA sequencing used to be crazy expensive. Take the early 2000 Human Genome Project. Sequencing one human genome took 10 years and $3 billion. To cut costs and time, scientists proposed new sequencing methods, including graphene-based ones. Scientists plan to laser drill nanopores in graphene, just big enough for single DNA strands. During sequencing, DNA passes through base by base. Each base creates unique electrical signals in the graphene, identifying its type. Reports say a company called Oxford Nanopore is collaborating with Harvard University to develop this graphene DNA sequencing tech. Success would eliminate complex processes and expensive gear, slashing costs so much you could sequence DNA at home. From fullerenes to nanotubes to graphene, though all carbon-based, each has unique miraculous traits proving invaluable across fields, showcasing nanomaterials magic. Take beyond materials, scientists are fascinated by nanoscale phenomena too. Next, let's explore two cool nanoscale properties: structural color and self-assembly. First, structural color. Color as in visual hue. This concept contrasts with pigment-based color from dyes. The vibrant looks of clothes, food, or products mostly come from pigments. That's relatively easy to grasp. So what exactly is structural color? Before discussing this nanoscale phenomenon, let's talk about an animal, the blue morpho butterfly. These butterflies are widely found in tropical regions like South America. Their most striking feature is the blue color of their wings. This blue has a metallic shimmer that's truly unforgettable. Because of this stunning color, the blue morpho has become a top favorite among butterfly collectors. But there's actually no pigment in the blue morpho's wings. Its beautiful colors come precisely from structural color. To better understand it, first some light basics. Each light type has a wavelength range. Visible light spans about 400 to 700 nanometers. When light hits similarly sized structures, it creates unique bending or scattering. Under advanced microscopes, the seemingly smooth wings reveal countless tiny tile-like structures. These microstructures are nanoscale and periodically arranged across the wing surface. Light striking these structures undergoes specific refraction and reflection. To our eyes, this creates that vivid blue color. So essentially, structural color comes from how nanostructures manipulate light. Structural color has many advantages. For instance, many pigments contain toxic heavy metals, while structural color achieves similar hues more eco-friendly. Plus, it resists fading. That's why researchers mimic it, like using butterfly wings as models to deposit nanoscale plastic beads on substrates. They electroplate gold or foil into bead gaps, then remove beads, creating periodic metallic nanostructures that display structural colors. Others use elastic polymers to produce structural color. Besides color generation, this material can stretch and bend. When stretched, its internal nanostructures shift slightly, changing the structural color. In 2012, a fashion designer wove this elastic polymer into fabric, creating clothes with butterfly ring-like brilliance.
Even better, want to change your outfit's color? Just give it a tug. Amazingly novel!
Besides structural color, another nanoscale marvel is self-assembly. Self-assembly means substances spontaneously forming ordered structures. It's everywhere in nature, like when separate DNA strands form double helices spontaneously. For its 125th anniversary, Science magazine listed 25 big questions for 21st century scientists. So, one was, how far can we push self-assembly? Self-assembly matters because it's a promising method for manufacturing materials and devices. And currently, making tiny devices involves two strategies: top-down, carving away material from larger blocks, and bottom-up, assembling small components into desired products. Think sculpture. Top-down is chiseling marble, bottom-up is molding clay. Self-assembly is the ultimate bottom-up approach. Industry mostly uses top-down methods, but they hit limits at extreme scales. Take cheap manufacturing, where photolithography machines are crucial. They etch nanometer-scale structures onto silicon wafers. Achieving nano-precision makes these machines cost hundreds of millions.
To cut costs, some propose using self-assembly instead.
In 2019, a U.S. team demonstrated molecular self-assembly for semiconductor production. They placed molecules just tens of nanometers long together, letting them move freely. In special chemical environments, they spontaneously form highly regular nanoarrays. By simply adjusting molecular composition and length, they produce pattern structures, even periodic arrangements resembling transistors. Oh, wow. Transistor. This work could revolutionize chip manufacturing. Both structural color and self-assembly prove a principle. Nanoscale phenomena can impact our macro world, even overturn industrial conventions. And as research advances, more nanoscale phenomena will solve macro world challenges. Now let's explore nanotechnology's contributions through real world problems. First, energy, undoubtedly one of today's most pressing issues.
Society runs on oil and electricity, yet shortages persist unresolved.
To produce more energy, some scholars propose a bold idea. Turning air into fuel sounds almost like a scam at first. But think, we harvest energy from air constantly through plants. Plants have long been humanity's primary energy source. Fruits for food, wood for heat, even oil. Coal, too, originates from ancient plants, yet soil contributes only 3% of a tree's mass. Those massive trunks and fruits, they're made from air and water, primarily through photosynthesis. Over billions of years, plants evolved to efficiently convert water and CO2 into sugars. Now, scientists aim to mimic this with artificial leaves. But unlike plants producing sugars, we want direct fuel compounds. Fuel composition is simple. Gasoline and kerosene are mainly carbon and hydrogen. CO2 provides carbon. Water provides hydrogen, both abundant in air. So, elementally speaking, this transformation is possible. But turning air into fuel requires two conditions: external energy and catalysts. Energy sources for artificial leaves vary. Light energy works, electricity works, with electricity coming from solar, wind, or other clean sources. Demonstrations energy alone isn't enough. Catalysts are essential for converting air to fuel. Catalysts dramatically speed up reactions to meet practical demands. Today's cutting-edge catalyst research focuses on shrinking them to nanoscale. In catalysis, only surface atoms actually participate. Atoms inside particles remain unused. At equal mass, smaller particles expose more surface area, meaning more atoms join reactions. This is crucial for certain catalyst materials. Platinum catalysts are the prime example. Platinum, as in platinum jewelry, is a costly metal. Beyond jewelry, platinum can extract hydrogen from water when electrified.
Though effective, platinum's cost prevents large-scale use.
So scientists developed methods to shrink platinum particles, maximizing catalytic atoms. Commercial platinum catalysts now measure around 3 nanometers. Some even achieve single-atom catalysts, approaching 100% atom utilization. In catalyst research, China leads globally. Take academician Li Can's team at CAS. They've long pioneered nanocatalyst improvements. Recently, they proposed the Liquid Sunshine Initiative. This plan uses solar energy to split hydrogen from water. Then catalysts help react hydrogen with CO2 to produce liquid methanol.
Methanol is both excellent fuel and vital industrial feedstock. Highly valuable.
In 2020, this system launched successfully in Lanzhou, Gansu. So, getting fuel from air isn't magic. It's reality already here. Beyond energy, health is another major concern. Nanotech truly shines in health, especially one exciting area: using it to guide stem cell differentiation. You've probably heard of stem cells. They're special because they can become various body cells, like muscle, skin, or bone cells. That's why some call them the body's raw materials. But here's a big question. How do stem cells know what to become?
Why do some from the same batch turn into muscle, while others become skin?
Cracking this could let doctors grow specific tissues and organs from stem cells, helping countless patients heal or recover from injuries. For this mystery, nanotech researchers might have an answer. First, cells constantly interact with their environment. In the 1970s, young scholar Donald Inger noticed cells deforming under force during culturing. He wondered if mechanical responses deserved more study. But back then, genetic determinism ruled, believing genes alone predicted all cell behavior. Crucially, precise control of cells' physical environment wasn't possible, so academia showed little interest. But Inger never gave up. Later, he met nanochemist George Whitesides, who developed ultra-precise nanoscale patterning on surfaces. So Inger and Whitesides teamed up, completing a landmark study in 1997. They created tiny bumps on flat substrates, some large, tens of microns, others small, hundreds of nanometers.
They then grew skin cells on these. Different bumps meant different mechanical stresses on cells.
Results showed cells grew normally on large bumps where forces were evenly distributed. But on small bumps with concentrated forces, cells died.
This experiment proved Ingber's original idea. Cells respond differently to mechanical forces.
Soon, research expanded to stem cells. One team created nano surfaces with different shapes, like rounded floral patterns. Another used sharp star shapes that placed stem cells under greater tension. Stem cells on star shapes turned into bone tissue, while floral patterns with relaxed forces became fat cells. This may explain why exercise, creating tension and compression, promotes bone growth in humans. Without exercise, weaker forces on stem cells produce more fat cells. Of course, applications don't always want differentiation. Sometimes keeping stem cells primitive is key. Researchers found a nano pattern, 120 nanometer wide pits spaced 300 nanometers apart. Stem cells here remained undifferentiated for 8 weeks. But damaging the pits triggered differentiation into bone cells. So controlling stem cell states via nano patterns holds many mysteries needing further exploration. Hopefully soon, scientists will decode how nanosurfaces dictate stem cell behavior, making them obedient tools. Need specific tissues or organs? Just command them to transform. Of course, Nanotech's life science applications go far beyond this. For more, check our previous book interpretation, Nano and Life. We've covered nanomaterials, nanoscale phenomena, and cross-field applications in this session. But what we've covered barely scratches the surface of this vibrant new field. The book for Though Nanotechnology Operates at Invisible Scales, its new materials and technologies will reshape our world like giants moving mountains, guiding humanity toward a brighter future. All right, that concludes our exploration of the giant of the infinitesimal. Find reading notes below the audio. See you next time.